Today, let's talk about intermolecular forces. Now, before we talk about them, let's first define what they are. So, intermolecular, we have, I'm spelling this wrong. No, that's right. Okay. You have intermolecular forces. So, inter means between. So you can kind of rethink of this as forces between molecules. Okay, so something that's worth noting is these are not chemical bonds. No intermolecular force is as strong as the intramolecular or the within molecule bonds that form. Okay, so first let's talk about something called electronegativity. Now this is a pretty simple thing to understand, but it's important that we know exactly what it is. So if we have a periodic table, something like this, kind of goes down a little bit, goes back up a little bit. Down here we have francium, and then we're going to ignore noble gases. So then over here we have fluorine. So if we were to look at the electronegativity, it goes something like this, where this is getting increasing electronegativity. Now electronegativity is just the, you can think of it as the ability or the tendency of an atom to attract an electron. So for example, if we had like carbon and carbon bound to each other, we have two electrons, and the electrons, we draw them in these Lewis structures as this line, but that's not actually what they are. They are in atomic orbitals. They're all around. And in carbon and carbon, they're the same atom, so they're identical, so they have the same electronegativity. So an electron is going to spend the same amount of time on either side. But that's not always the case. We have something like hydrogen over here. Let's see what happens when we bind that with fluorine. Well, what we're going to see is something that looks like this, where the electrons spend way more time with the fluorine atom because the fluorine is a lot more electronegative. So it says, that's mine, I'm taking it. And and the hydrogen, it's not very electronegative, so it says, that's okay, I didn't want that anyways, so that's kind of what happens. So you can kind of see the first type of bond already is what happens when there's a large difference in electronegativity. Well, one atom is going to outright take the electron from another. So, for example, if we have sodium chloride or table salt, that's actually sodium plus chlorine minus. The sodium donates an electron to the chlorine because the chlorine is more electronegative. So then you'll have two ions, because remember, we can find the charge by we take the number of protons minus the number of electrons. So this would have one less electron than the neutral atom, so it would have a positive charge. And this would have one more electron than the neutral atom, so it would have a negative charge. And then we're just looking at the electrostatic interactions between them to form the bond, where positive positive charge and a negative charge will attract together. So this is called ionic bonding, and it's named quite appropriately because a charged particle is called an ion. So this here is a positive charge, so that's a cation, and this is a negative charge, so that's the anion. So, and just for clarification's sake, positive charges are always cations, negative charges are always anions. That's what they mean. An easy way to remember this is you can think of this as the A for N for negative, and then you're just left with ion. So a negative ion, anion. Cation you can just kind of think of as not an anion, or I've heard some people say cats are a positive thing, so you can think of that if you are someone who likes cats. Okay, so let's see here. Let me erase this. My eraser does not seem to be very good today. Probably to clean that out somehow. Okay, so we have our first intermolecular force is ionic. We're just going to say it's an ionic attraction. So what do we need to know about these? Well, put a subpoint, or I should have a different numbering scheme here. Let's put this. So they are very strong. That's the first thing you need to know about them. And they're actually so strong that they're kind of misplaced in a manner of speaking. Ionic bonds are, I just gave it away, they're actually considered chemical bonds. They're an ionic bond. So that's a good thing to know. That's how strong they are. I have some notes here, so I'm gonna make sure that I'm not forgetting anything important. Oh, and by the name, you can tell an ionic bond requires ions, which makes sense. Okay, so now let's talk about something else that might not be super obvious at first, but kind of makes more sense when you start to see it. Let's see here. So we're going to talk about something called the London dispersion force. So what does that mean? So let's say we have some molecule, doesn't really matter what it is, let's just put like some carbon. Hydrogens, hydrogens, hydrogens. Let's put a couple carbons here. Okay, so here we have some propane. Nothing special. So propane is neutral, right? Everything's balanced out. Hydrogen has its 2 electrons, valence is flowed. All the carbons have 4 bonds, so they all have 8 electrons, their valence is filled. So they're all good to go, they're all neutral. No charges to speak of in this representation. So one of the drawbacks of Lewis structures is that they're static. So we look at this and we just say, oh, that's propane. But what's actually happening isn't just that the electrons are making these little lines and they're just hanging out. They're actually still orbiting. The orbits change as bonds are made, but they're still orbiting. So at any given point, let's say this one here, maybe the electrons are more on this side. So this side is partially negative. So this is gamma. It's a Greek letter. And when you see gamma with respect to like charges, you can just think partial. So the electrons might be more on this side. Well, then we have a partial positive charge here. Well, this partial negative charge is going to repel some of the electron density on this carbon. So now this has a partial negative, partial positive, and so on and so forth throughout the molecule. So these types of attractions, and then I guess I should also mention that then this can form between molecules. So if I had another molecule of propane, I'm going to leave out the hydrogens just for clarification's sake. But let's say, if I did this, if this had an induced dipole, well then they could kind of form a it's not very strong, but it does exist. It's an interaction that's between the dipoles, the induced dipoles. So this is the London dispersion force. It's also called van der Waals force, or the induced dipole effect. And that's all it is. It's just taking into account that electrons are actually moving throughout a particle at any given time and aren't static. So that's the second force. Actually, I think I did these out of order, because if I wanted to do them in decreasing strength, London dispersion forces would actually be at the bottom of the list. They are not very strong. And it makes sense. It's not a true dipole or an ion. It's just kind of there. Something to note is that London dispersion forces, if I had, let's say, a longer carbon chain, the London dispersion force for that type of molecule interacting with itself would be much greater than, just for like propane, methane, ethane, which have 3, 1, and 2 carbons respectively. So I'm just going to put this over here for now, or I'll leave a little bit of space. I'll be ranking them later. So this is the London dispersion forces. Or LDF. So that's a good one to know. Now we can talk about something that's related to the London dispersion force, but a little even easier to comprehend, I would say. And this is just dipole-dipole interactions. So let's look at water. We all know what water looks like. HOH, right? And then you may or may not know this, but in water, there's 2 lone pairs of electrons on the oxygen. So this oxygen is more electronegative than hydrogen. So as such, it'll have a partial negative charge, and the hydrogens will have a partial positive charge. So what happens if we put another molecule of water over here? Well, we can see pretty right away, we can kind of see these interactions starting to form. So here we have a dipole, and I should just point out that the dipole comes from here. I believe I remembered that notation correctly, where the positive is over here. So if we were to look at what's called the dipole moment, that's pretty much just looking at where the charge is in the molecule and in what orientation. This is telling us that we can look at almost as if there's like a plane of symmetry, and over here, so these are their charges cancel out, you can think of. So there's charge here and charge here, they're the same though. But there's more positive charge down here, and then negative charge up here. So it has what's called a dipole moment. So you can think of a dipole moment as anything that has charge. Generally, anytime that there's a difference in electronegativity, you have a dipole moment. So they're quite common in molecules. Water is a really great example though, because we see it all the time. So here's an example, and then I'll draw the dipole moment here as well. So there's that, and they will bond. So dispersion, or dipole-dipole attraction, they require polar covalent bonds. So that just comes from over here. You can see there's a polar bond because there's a difference in electronegativity. And let's see. I'm just looking at my notes to make sure I don't forget anything. So they require a polar covalent bond. Let's see. I'm just going to write down their name here. And as the numbering here is suggesting, as I had mentioned earlier, these are the weakest, these are the strongest. These here, they're a little in between. They're significantly stronger, generally speaking, than ODF, but they are weaker than ionic attraction. And again, they require a polar covalent bond, and they work just based on dipole interaction or just electrostatics. Okay, and now let's talk about a very, very famous type of intermolecular force. It's something of a little bit misnamed because it is not a bond, but that's what it's called, so that's what I'm going to be referring to it as. This is hydrogen bonding. All right, so I'm just going to look at this here real quick because I have a nice little example drawn out. I would just like to repeat that. Let's see. Oh, I actually already showed you hydrogen bonding, because hydrogen bonding is kind of a special case of dipole-dipole interaction. Water is a great example of hydrogen bonding. So hydrogen bonding is when we have an OH, NH, or FH bond in one molecule, and then we also need an O, N, or F molecule or as a part of the second molecule. And so then you'll just have something that looks like this, where there will be some molecule that will have, you know, anything of O, N, or F. I'm just kind of drawing these little brackets to indicate it could be anything in there that'll be bound to hydrogen. You'll have a intermolecular interaction with either of the O, N, or F. And these just do with the electronegativity of these ions. It just makes that bond particularly strong, is how you can think of it. Nice way to remember that. You can think that chemistry is fun, but if you say that slightly, wrong, then it's fun, F-O-N. So there you go, there's that. Okay, and that there is the fourth of the intermolecular forces. So something that is worth noting is that most of these forces arise due to electronegativity. So it's something that you hear about and it doesn't really sound all that important, but it is incredibly important. So, and the periodic trend for electronegativity, again, is going up like that, where you have fluorine over here, francium down here. So let's see, I believe that's everything I wanted to discuss today. So if there are any questions or comments, please feel free to reach out, and I will do my best to make sure that the material is understandable and that you have all the knowledge you need to talk about these forces. Yeah, so have a good day, and teaching some more chemistry. Thank you.